Okay guys, I welcome you all to Engineers Academy. Do subscribe my channel if you haven't done it yet. Now we are going to solve this problem which says that the 100-pound uniform square plate is supported by a ball and socket joint at O. We have this square plate which is 36 by 36 inches and it has a weight of 100 pounds and it is supported by this ball and socket joint at O and this cable EF and a fixture at A which can support vertical force only and a linear spring at C. So at C we have this linear spring which has some stiffness K, and it is said that if the unstretched length of the spring is 6 inches, determine the spring constant K required for equilibrium in the position shown. So the unstretched length of the spring is 6, and as we can see that this spring is stretched to a distance of 10 inches. So as we know that the spring force is, let's say that the spring force is equal to K, that is the stiffness times the change in length. Now K is required, K is not known, and the change in length is, the stretched length is 10 inches and the unstretched length is 6. So 10 minus 6 is 4, so we can say that the spring force is equal to 4K, and this is in pounds. Now we have to find the spring stiffness, and the plate is in equilibrium, right? So at point E, if we cut this cable, so we will have that tension T in the rope, which is going to act in this direction from E to F. Similarly at O, since we have a ball and socket joint, so we will have the OX reaction. Here we will have OX, let's say. Then we will have OY reaction, that is in the positive Y. Let's say this is my OY. And then we will have the OZ reaction. Let's say that OZ reaction is acting in the positive Z direction. So this is OZ. And now at C we will have the spring force which is going to act in this direction. This is the spring force. This is Fs. And at A, it is said that a fixture at A which can support the vertical force only. So let's say that here we have the AZ reaction only in the vertical direction. So this is AZ, and this is that tension T. So first of all, we have to find this Cartesian vector representation of this tension T which is acting from E to F. So now as we know that T vector, this T vector will be equal to its magnitude times the unit vector from E to F, and now this magnitude and the unit vector from E to F is the position vector from E to F divided by its magnitude. Now this is equal to, now the position vector from E to F can be determined by moving from E along X, Y and Z to reach that point F. So from E we need to move 18 inches distance in the negative X. This is the positive X direction, so we need to move 18 inches in the negative X. So this is T magnitude, and in the negative I we need to move 18 inches, and then once we reach here then we need to move from here to here. Let's say if I drop a perpendicular, so we need to move this distance. So from this origin this distance is 16 inches and the plate is 36 by 36. So 36 minus 16 is 20. So from here to here this distance is 20 inches. So let's say that this point is, let's say point E. Let's say this is point G, let's say. So this BG length is 20 inches. So we need to move 20 inches in the negative J, and then once we reach here then we need to travel 16 inches distance in the positive K. So this is plus 16 in the positive K, and then the magnitude of this position vector will be 18 square plus 20 square plus 16 square under the square root. So this magnitude is 18 square plus 20 square plus 16 square. This gives us 31.305 approximately. So this magnitude is approximately equal to 31.305 305 inches. And now that Cartesian vector representation of this t is equal to, if we multiply this t inside, so we will have minus 18t divided by that magnitude, it is 31.305. Then we will have minus 20t divided by 31.305, similarly plus 16 divided by 31.305 k. So now 18 divided by 31.305, this gives me 0.575. This is minus 0.575 t. Then minus 20, that is 20 divided by this gives me minus 0.639. This is 0.639 t, and then 16 divided by, that is 16. This is equal to 0.511. 0.511 into t. This is t. Okay. So this is the Cartesian vector representation of that tension t. So this t has one component which is acting in the negative x. This is minus 0.575. This is tx. Then we have negative component in the y direction. This is that ty. This is tx. This is ty. And this is tz. So tz is acting in the positive z direction. Let me show that. So this is tz. This is tx, this is ty, and this is tz. So now, since the system is in equilibrium, so if I apply the summation of moment about point A, I am going to solve this by vector analysis, right? So the summation of moment at point A, this will be equal to 0. And then we have to find the moment of this Fs, this tension T, and this O reaction, right? So first of all, we have to write the moment of this tension T. So for the moment about tension T, we have to define the position vector. And that position vector or the moment arm will be from A to E. So we can write that the moment produced by the tension T will be the position vector from A to E cross that T vector. Then we will write plus the moment due to that reaction at O. So this position vector will be from, this will be the moment arm from A to O. So now we can write that the position vector from A to O and cross product with that O vector. So now this O vector is, you can say that this O resultant of this OX, OY, and OZ, that will give us the Cartesian vector representation of this reaction at O. So that will be OXI plus OYJ plus OZK. Similarly, the moment due to this spring force, again we have to define one another moment arm or the position vector. So this position vector will be from A to C. So now I will write plus position vector from A to C cross that spring force and the vector of that spring force. So now the spring force is only acting in the positive x direction. So if we represent that spring force as a Cartesian vector, so we will have Fs in the positive I plus 0j plus 0k, since the spring force is only acting in the positive x direction. And then we have the weight of this plate. The weight of the plate is acting at the center of this plate, at its geometric center. So we will have that weight somewhere here at the midpoint, and let's say that it is acting at point M, let's say. So its moment or its position vector from A will be AM, right? Let's say like this. So let me write that the moment due to that weight will be the position vector from A to M cross that vector, that weight vector, and this will be equal to 0. Now the weight vector is, let me write that the weight vector, since the weight is vertical, right? This is the weight vector. So its I component is 0, its j component is 0, and it is acting in the negative k direction, so we will write minus 100k. The weight is 100 pounds. So now we have to find this position vector from A to E. So let me write that this is a determinant. So this is I, j, and k, and the position vector from A to E. So to find the position vector from A to E, we need to move 36 inches from A to B in the y direction. So this is plus 36, and then we need to move 18 inches in the positive x. So I will write plus 18, and there is no need to travel in the k, so this is 0k. So the position vector from A to E is 18i plus 36j and 0k. Now the tension T, we have this tension T. This is minus 0.575 T. Let me write it is minus 0.75 T. Now the J component of that tension T is minus 0.639 T, and the Z component is, let me write it here, is 0.511 T. And similarly we will write plus. Now the moment due to that O vector, that is the reaction at O, so this is again I, j, and k. Now the position vector from A to O. So from A we need to travel this much distance from A to this point. So this distance is 36 minus 6, so this is 30. So along I we need to move 30 inches, and then along Y we need to move 12 inches. So along J we need to move 12 inches, and there is no need to travel along K, so this is 0. And then O, the components of O are, that is OX, OY, and OZ. These are not known. Then plus the RAC, I, J, and K. Now the position vector from A to C. So from A we need to travel 36 inches in the positive x. This length of the plate is 36. This is 36 by 36 plate, so we need to move 36 in the positive x and then 36 inches in the positive j to reach that point C and 0k. And similarly the spring force is, this is the spring force, so this is Fs, 0 and 0. Similarly this is plus, and now the position vector from A to M, and M is the midpoint, the geometric center of this plate. So from A we need to move half of the length. So the half length is 18, so we need to move 18 in the x, so 18 inches, and then from there we need to move 18 inches in the positive y, so that is 18, and k is 0, and this is the weight vector. This is 0, 0, and minus 100, and this is equal to 0. Now we have to find all these determinants one by one. So let's say that we have to hide this and this. So with I there is always positive sign, and this is 36 into this. So let me find 36 into 0.511. This gives us 18.396 T, 18.396 T. This minus 0, so this we will get this. Then with J we always have minus sign, and then for J we need to hide this. So this is 18 into this, 18 into 0.511, 18 into 0.511. This gives us 9.198, 9.198 T, and then this is 0. So 18 into this minus 0, and then for k we have to hide this plus k. This is 18 into this. We write 18 into minus 0.639. This gives you minus 11.502 minus 11.502 t, and then minus 36 into this. So minus 36 into minus 0.575 t. So let me find this. This is 36 into 0.575. So this gives me 20.7, and this minus into minus will become plus. So this is 20.7 t plus 20.7 t. And now we can add both of these. So this is minus 11.502 plus 20.7. So this gives me 9.198 t. 9.198 t. Now we have to find this determinant. This is again we have to hide this and this. So again we have plus I, and then 12 OZ and minus 0, then minus J 30 into OZ and minus 0, and then we have this, so plus K and 30 OY minus 12 OX and similarly we have to find this determinant now. So for that we have to hide this and this. So this is plus I again, and this is 36 into 0, 0 minus 0, so this will give us 0. And then for J we have to hide this. This is minus J, 36 into 0 minus 0, so this is again 0, and then plus K. So for K, this is 36 into 0 minus 36 into Fs, minus 36 into the spring force. Now we have to find this last determinant, which is again plus I. So for I we have to hide this and this. This is 18 into minus 100 is minus 1800, minus 0, then minus J, then again minus 1800 minus 0, so minus 1800, and then plus K. So for K, this is 0 minus 0, so this is 0, and all these summation will be equal to 0. So now we have to add up all the I terms, J terms and K terms, so that will be the summation of the moment about the x-axis, the summation of moment about the y-axis, the summation of moment about the z-axis. So now the summation of moment about the x-axis, so we have to add up all the I terms. So this is 18.396t plus 12 OZ plus 0 minus 1800 equals to 0, or we can say that this is equal to 1800. Similarly, the summation of moment about the y-axis, we have to add up all the j components. So this is minus into 9. Let me write minus 9.198 t, then minus 30 OZ, then minus 0 and minus into minus plus 1800. This is equal to 0, and if I bring this 1800 to the other side of equation, so it will become negative. This is minus, and now if you multiply this whole equation with minus, so everything will become positive. So now we have these two equations. So now if I multiply this equation, let's say this is equation 1 and let's say this is equation 2. So now if I multiply this equation 2 with 2, so that is 9.198 multiplied by 2. This gives me 18.396, 18.396t plus 2 into 30 is 60 OZ, and 1800 into 2 is 3600. And now if I subtract this equation from this equation 1, so that is 18.396T plus 60 OZ 3600. So I need to subtract this equation. So this is plus minus minus plus minus. This will cancel out, and this is minus 60 plus 12. So this is minus 48 OZ equals to minus 1800. Minus will cancel out, and OZ is 1800 divided by 48. So 1800 divided by 48 will give us the magnitude of OZ, that is the component of the reaction at O in the Z direction. So this is 37.5. So OZ is 37.5 pounds. So now if I substitute this OZ in this equation, so we will get T. So T equals to 3600 minus 60 OZ, which is 37.5 divided by 18.396. So this is 3600 minus 60 into 37.5 divided by 18.396. This gives us 73.386. So this T, the magnitude of the tension T in that cable is 73.386 pounds. Now we can find, when we know this T, we can find Tx and Ty. So if we put the T value in this equation, so we will be able to find this T Cartesian vector. So this is minus 0.575 into T magnitude, which is 73.386. This gives us 42.197 minus 42.197, and this is in the I, this is in the J. This is minus, this is in the I, and then 0.639 multiplied by 73.386. This gives us 46.894. 46.894 in the J, and this is 0.511 multiplied by 73.386. So this gives us 37.5. So this is 37.5 K. So this is the Cartesian vector representation of the tension T in that rope. So now if we apply the summation of forces along X, summation of forces along Y, that will be equal to 0. So as we can see that the OY is acting in the positive Y direction, so I will write OY, and then this TY is acting in the negative Y, so this is minus TY, and there is no other force or component in the Y direction, so this is equal to 0. And from this we can say that OY is equal to TY, and we have already determined that TY, which is 46.894. 46.894. This is 46.894 pounds. Similarly, if we apply the summation of forces along the x-axis, so this is equal to 0, and along the x we have this Tx, we have this Ox, which is acting in the this is acting in the positive direction, since we have assumed that this is acting in the positive. Here in the determinant we have assumed that this is acting in the positive, since this is positive Ox. So we will write that this Ox is acting in the positive x. This is Ox minus the Tx, and this Fs is acting in the positive x. So first let me write that Ox plus Fs minus Tx, this is equal to 0, and if I bring this Tx to the other side of the equation, so this will become positive, and we know Tx is this. This is 42.197. This is magnitude is 42.197. So this is 42.197. And now if we add all the k terms in this determinants, right, in the moment about point O, if we find the summation of moment about the z-axis, so let me write the summation of moment about the z-axis is equal to 0. So we have to add up all these k terms. So this is 9.198 t, and this is plus 30 oy minus 12 ox minus 36 fs, and then 0. So this is equal to 0. Now we know t, so we have to multiply this 9.198 with that t value, which is 73.386. Then oy, so oy is equal to ty, so we have to replace this oy by that magnitude. This is 46.894. So now we have to find this constant. This is 9.198 into 73.386 plus 30 into 46.894. So this gives us 2081.824. So 2081.824, and this is minus 12 ox minus 36 fs. This is equal to 0. And if I bring this to the other side of equation, so we will have it minus 2081.824. And if I multiply this whole equation with minus, so this will become plus, plus, and plus. And now if I multiply this equation with 12, so we will have 12 ox. Let me write, we will have 12 ox plus 12 fs, and 12 into 42.197. So we need to subtract this equation from this one. So this is 12 ox plus 12 fs equals 12 into, first let me find this, 12 into 42.197. This gives us 506.364. 506.364. So now I have to subtract this lower equation. So this is plus, minus, this minus. So this will cancel out, and 36 minus 12 is 24 fs, and this is 2081.824 minus 506.364. This gives me 1575.46. 15. And now the spring force is equal to 1575.46 divided by this answer divided by 24. This gives me 65.644. And we have determined that the spring force is equal to 4k. That is the stiffness times the change in length. So the stretched length is 10 and the unstretched length is 6. So 10 minus 6 is 4. So the spring force is 4k. So now we have to write the spring force as 4k. This is 65 point. This is in pounds. And now the spring stiffness will be k divided by 65.64 divided by 4. So this answer divided by 4 is 65.64 divided by 4. This gives us 16.41. So k value is 16.41, and this is pound per inch. So this is that spring stiffness which is required to maintain this 36 by 36 plate of weight 100 pound in equilibrium. So this is the solution of this particular problem. I hope this will help you in your learning. Do subscribe my channel for the solution of such more problems from engineering statistics.